XCast.com.
Good morning, everyone. Welcome back to XCast, your weekly podcast for all things tech, all things games, and software related. Today we have a very special guest, the CEO of OS.com, the creator of the now famous Hub OS. Please help me welcome engineer Vince Retutal. Give him a round of applause, please. Engineer Vince is here to explain one of the intricacies of developing operating systems, mainly multiprocessor scheduling and real-time scheduling. I will leave the explanation to himself and his team of engineers. Take it away, Sir Vince.
Thank you for having me, Joaquin. So, I hope you're all having a good day wherever you are listening to this podcast. Once again, I am Engineer Vince Retutal, CEO of OS.com, with my team developing HubOS. Now, I am sure you have heard of uniprocessor scheduling, but we're not going to be discussing about that. In instances where the intensity of the workload demands it, or it is high enough but input-output on other functions is not required, it would be much more efficient to use multiprocessor systems. With multiple processors in the system, the load sharing becomes much more feasible, but it makes scheduling much more complex. So my team is going to be discussing about that and talking about the ins and outs of it. We'll now begin with my first engineer.
Good morning, everyone. My name is Joaquin Resus, and before we can talk about multiprocessor scheduling, let's first talk about what a multiprocessor system is. So a multiprocessor system is an organizational technique in which two or more processor units are employed in a single computer system to increase the performance of the system in its application environment compared to a single processor. Multiprocessor systems can be used in modern computer operating systems. So while rare, some of you have only one processor, I'm pretty sure, with multiple cores. Some computers do support multiple processors, like Windows. If you have Windows, then you may use multiple processors in that system. I don't know why, but some people use it for things like rendering, which is a third point here. More processing power generally results in faster tasks and multiple things to complete. Satellites also use this. They have a lot of processors in them to process a lot of data and do different things. And video games, while this is really rare, some video games do support multiple processors, and well, yeah, generally a multiprocessor system is just something that'll make things go faster because of its multiple processing power. So before we get into some of the types of multiprocessing scheduling, we first need to discuss the types of multiprocessor systems. So the first is a loosely coupled processor, the second is a tightly coupled multiprocessor, and the third is functionally specialized. So loosely coupled is also known as distributed memory, and this is where each processor, as you can see in this diagram here, where each processor, denoted by the letter P, has their own local memory, LM, and I/O input. So each processor is in charge of a specific I/O and is in charge of their own local memory as well. The way these processors are coupled into computer modules. So this is computer module 0 until n-1. And these computer modules, when they communicate with each other, they communicate through a message transfer system, as you can see here, which is also denoted with the MTS. The next is the complete opposite of the loosely coupled processor, which is the tightly coupled multiprocessor. This is also called shared memory. If loosely coupled had distributed memory because they had their own local memory, as you can see here, that the tightly coupled multiprocessor has a shared memory. And at the bottom here, you can see the memory modules, separated of course, but they go through a memory channel which is accessed by all processor systems. So in this diagram you can see here, there are two processor systems that access the memory channel, which is the interface between all memory modules. And it also has all I/O inputs. It also shares the I/O inputs compared to back then, where in the loosely coupled they have dedicated I/O channels to each of the computer modules. Right here, it's all I/O channels accessible by all processors at the same time. One limitation for when processors attempt to access the same memory unit. So naturally, if the processors will attempt to access one memory unit and one memory module right here, and both of them have a need for that memory module, then naturally the second process will have to wait until that memory module is done being used before it's being accessed. So in a way, this will be sort of slower than loosely coupled if you have a lot of processes that require accessing the memory, especially if they're accessing the same memory module at the same time. Last but not least, it's the functionally specialized processor. So from the name itself, it's functionally specialized for a certain task and is controlled by a master processor. So in this diagram over here, it shows an I/O processor, which is in charge of all I/O inputs. Right here, as you can see here, all the peripheral devices are connected to the I/O bus, which is connected to the I/O processor. The I/O processor is then controlled by the central processing unit, which is its master processor, and they both access the memory unit at the same time. So this is the main difference between this and the loose and the tightly coupled processors. So now that we're done with that, let's talk about parallel computing. This is very important if you want to talk about multiprocessor scheduling and real-time scheduling. So parallelism, or also known as parallel computing, is a type of computation in which many calculations are performed at the same time. It is divided into different types of parallelism by granularity or grain size. Granularity or grain size is the measure of the amount of work performed by a task. There are different types of parallelism differing in granularity, and I will discuss these in detail in just a moment. So firstly, it's independent parallelism. Second, coarse parallelism. The third is very coarse-grained parallelism. These two, coarse and very coarse, can be interchanged. They are almost one and the same, really. There's not much difference between them at all. Medium-grained parallelism and fine-grained parallelism. Fine-grained parallelism is the parallel computing type that has the tiniest granularity. Medium-grained is the middle ground between coarse and fine-grained. So first, independent parallelism. Independent parallelism means that operations in a query do not depend on one another and are therefore executed in parallel. What this means is that operations and processes do not require the finishing of another one to proceed. So they can work independently from each other, and they are, if you have multiple processors, they can be done with the said multiple processors. So for example, in this diagram over here, you can see that operation 1 has absolutely no relation with operation 2 and its constituents. So process, the data fragment here, the data fragment here, is not going to be related to operation 1 or 2 or vice versa. So processor 1 is in charge of operation 1, processor 2 is in charge of operation 2, and so on and so forth. So it's pretty simple to understand. The second type is coarse or very coarse-grained parallelism. So I'll explain this image in a bit, especially when we get into medium and fine-grained. But coarse and very coarse-grained is relatively large amounts of computational work done between synchronization events. Synchronization among processes is at a very gross level. What this means is that if you imagine an organizational chart in a company, for example, there is the CEO and their managers and the people working under those managers and the people that work under those people that work under those managers. So you could think of the coarse and very coarse-grained parallelism as at around the managerial level, where they have a bunch of processes that are under them, but this is coarsely defined. So that means that it's a high level of computing, which means it has a lot of computational work because each of the grains in coarse-grained parallelism has a bunch of fine-grained tasks that are within them. The second is medium-grained parallelism, or the compromise between coarse and fine-grained. This is called the compromise because it's around the middle level. If we're talking about that organizational chart that we were discussing just a few minutes prior, this is around the middle level of that point. So it's not that fine, it's not that specific yet, and it's also not that high in the level. So it's smaller than coarse-grained, but it's bigger than fine-grained. So it still handles a lot of sub-processes under it, but it requires less computational power than coarse-grained, just because it has smaller grains. And last but not least, it's the fine-grained parallelism, which is used for highly parallel applications and is very specialized. The reason that it's very specialized is, as you can see here, it's very, very specific. It is already at the lowest level of the organizational chart, where you're handling every single task or every single thread, as you can see here. See, as this image further explains that coarse-grained. So how coarse-grained has a bunch of threads inside it, and then when you do fine-grained, you're dealing with those individual threads by themselves, which means that there's going to be a lot of input if you're doing fine-grained parallelism. But that's not too bad in a sense. And that is it for my report. The next person that will be covering the next topics will be our very own CEO and head engineer, Vince Retutal. So kindly take it away, and thank you for listening.
Good day to everyone again, and I hope you're all comfy while listening to this podcast. So I'll be discussing key topics on multiprocessor scheduling, specifically on synchronization, granularity, and processes, scheduling, design issues, assignment of processes to processors, static assignment, master-slave architecture, and peer architecture. So, when dealing with multiple processes and processors, it is important that we determine the synchronization granularity in order to optimize a current system to run much more efficiently depending on the task and workload. So, based on this table, we determine a grain size to be fine if the synchronization interval is less than 20 instructions. So, by definition, parallelism inherent in a single instruction stream. For medium, it's 20 to 200, and it's described as parallel processing or multitasking within a single application. And for coarse, multiprocessing of concurrent processes in a multi-programming environment, and it is determined to have 200 to 2000 instructions for its synchronization interval. And for very coarse, it's described as distributed processing across network nodes to form a single computing environment with 2,000 to 1 million instructions. And for independent, it's multiple unrelated processes, and therefore it is not applicable. To reiterate, when dealing with fine parallelism, this is inherent in a single instruction. So it represents a much more complex use of parallelism than is found in the use of threads. In a medium grain size, it is referring to its support to the parallel processing or multitasking within a single application. Take note that a single application is a collection of threads, and these threads usually interact more frequently. If it is then coarse, there is synchronization among processes similar to very coarse parallelism at a very gross level. It is similar to running many processes on one processor, except that it's more spread out to more processors, and it's multiprocessing. Similarly, if it is very coarse or in very coarse parallelism, there is synchronization among processes, but at a very gross level. It's good when there is no infrequent interaction among processes, so distributed processing across network nodes to form a single computing environment. Lastly, in independent parallelism, each process represents a separate and independent application or a job running. It is often used in time-sharing systems. So, to give you an idea as to how knowing these can really help in real-life applications, take for example mobile applications. Mobile processors and mobile SoCs usually operate with a distribution between high-power cores for more single-threaded tasks and low-power, high-efficiency cores. However, some systems often work best when it is assigned to a single processor, like sound mixing or audio mixing, as using multiprocessing systems would only add little to no benefit while introducing unnecessary complexity and cost. There are also applications that can be run as they are threaded on one processor, but performance can increase drastically when it is spread out over multiple processors. This can be seen in content creation and heavier workloads such as 3D or scene rendering. So this is the thread structure for a rendering module. As you can see, the skybox, the main view, the monitor, and other key components work under the render. The scene list which contains objects that each have their own particles and characters, are all situated under the main view. Next, we go to scheduling design issues. So in scheduling for multiple processors, you would often have to deal with three unrelated issues: assignment of processes to processors, use of multi-programming on individual processors, and actual dispatching of processes. So among these three, the approaches that would have to be taken would then depend on the degree of granularity of applications and the number of available processors. So this connects with the next subtopic, which is the assignment of processes to processors. I will now hand over the specific portion our surprise guest, Jordi L. de la Cruz, with his expertise fitting in.
Thank you, Engineer Vince, for having me. Assuming all processes are equal, it is simplest to treat processors as a pooled resource and assign process to processors on demand. So the next step then is to decide whether the assignment should be either dynamic or static. In dynamic assignment, threads are moved for a queue for one processor to queue for another processor. However, in a static assignment, you would have to permanently assign processes to a processor. So, doing that would result in dedicating short-term queue for each processor, less overhead, and allowing the use of group scheduling. But note that having it static can leave a processor idle, so you would have to need to use a common queue. Though even among the dynamic and static assignments, there are still various methods required. You can use a vast spectrum of approaches, but among them the most known ones are using the master-slave infrastructure or the peer architecture. Back to you, Vince, and thank you for having me.
So thank you for that brief but quite insightful explanation, Engineer Jordi. So, in a master-slave architecture, the master is solely responsible for the scheduling, while the slave sends service requests to the master. The key kernel functions always run on a particular processor. This approach can be disadvantageous because the failure of the master means the shutdown of the whole system. It also means the master can become a serious performance bottleneck. However, in some very primitive systems and applications, it can be the contrary and can actually improve performance, though the primary advantage of the master-slave architecture is its simplicity. Now for peer architecture. It's different in that the kernel can execute any processor, and each of these processes can do their own self-scheduling. However, it can complicate the operating system if multiple processors are assigned identical processes. So make sure that two processors do not choose the same process. So thank you for listening. So from Engineer Retutal and Engineer Jordi, we thank you for listening.
So the next couple of topics will be discussed by Engineer Jonino Velasquez and Kenneth Igot. I will now hand the floor over to them right now.
Thank you for inviting us here at the XCast podcast, Mr. Retutal. It's really a great pleasure for us to talk to you about different types of scheduling in the operating system, mainly about process scheduling and thread scheduling. So what is process scheduling? Process scheduling is an operating system task that schedules processes of different states like ready, waiting, and running. Process scheduling also allows the operating system to allocate a time interval of CPU execution for each process. Another important reason for using a process scheduling system is that it keeps the CPU busy all the time. Process scheduling queues. It helps maintain a distinct queue for each and every process states and PCBs. All the processes of the same execution state are placed in the same queue. Therefore, whenever the state of a process is modified, its PCB needs to be unlinked from its existing queue, which moves back to the new state queue. There are three types of operating system queues: job queue, ready queue, and device queue. Job queue helps you to store all the processes in the system. Ready queue helps you to set every process residing in the main memory, which is ready and waiting to execute. Lastly, device queue is a process that is blocked because of the absence of an I/O device. Here shows the diagram of how process scheduling works. The rectangle shape represents a queue, the circle denotes the resource, and the arrow indicates the flow of the process. At number 1, every new process first put in the ready queue. It waits in the ready queue until it is finally processed for execution. Here, the new process is put in the ready queue and is waiting until it is selected for execution or it is dispatched. At number 2, it shows that one of the processes is already allocated at the CPU and it is executing. Number 3 shows that the process should start issuing an I/O request. And at number 4, the process should now be placed in the I/O queue. And number 5, the process should create a new subprocess. Number 6 shows that the process should be waiting for its termination. And number 7, it should remove forcefully from the CPU as a result of interruption. Once interrupt is completed, it should be sent back to the ready queue. This is the two-state process model of a process scheduling. Running and not running. Running in the operating system, whenever a new process is built, it is entered into the system which should be running. While not running is a process that are not running are kept in a queue which is waiting for their return to execute. Each entry in the queue is a point to a specific process. Scheduling objectives. Scheduling objectives maximizes the number of interactive users within acceptable response times. It achieves a balance between response and utilization. It avoids indefinite postponement and enforce priorities. And it also should give reference to the processes holding the key resources. Types of process schedulers. The process scheduling is the activity of the process manager that handles the removal of the running process from the CPU and the selection of another process on the basis of a particular strategy. There are mainly 3 types of process schedulers: long-term or job scheduler, short-term or CPU scheduler, medium-term scheduler. Here, long-term scheduler brings the new process to the ready state and it controls the degree of multi-programming. Short-term or CPU scheduler is responsible for selecting one process from ready state for scheduling and it is on the running state. And number 4, medium-term scheduler is responsible for suspending and resuming the process and it mainly does swapping. Thread scheduling. Thread scheduling is the thread execution that is separated from the rest of the definition of a process. It is an application that can be a set of threads that cooperate and execute concurrently in the same address space. On a uniprocessor, threads can be used as a program structuring aid and to overlap I/O with processing. In a multiprocessor system, threads can be used to exploit through parallelism in an application. Dramatic gains in performance are possible in multiprocessor systems. Small differences in thread management and scheduling can have an impact on applications that require significant interaction among threads. Scheduling of user-level threads to kernel-level threads via lightweight process by the application developer. Scheduling of kernel-level threads by the system scheduler to perform different unique operating system functions. Lightweight process is a thread that acts as an interface for the user-level threads to access the physical CPU resources. Contention scope. Control scope defines the extent to which contention takes place. Contention scope. Process contention scope is when the contention takes place in the same process. System contention scope refers to the contention that takes place among all the threads in the system. There are advantages between the process contention scope and the system contention scope. The advantage of PCS over the SES are it is cheaper, it helps reduce the system calls, and it achieves better performance. If the SES thread is a part of more than one allocation domain, the system will have to handle multiple interfaces. PCS thread can share one or multiple available LWPs, while every SCS thread needs a separate LWP. Therefore, for every system call, a separate KLT will be created. Approaches to thread scheduling. There are 4 approaches for multiprocessor thread scheduling, which are load sharing, gang scheduling, dedicated process assignment, and dynamic scheduling. Since Mr. Igot will be reporting about the 4 types of approaches to thread scheduling, I will have my little or basic knowledge about load sharing. Load sharing is a process that are not assigned to a particular processor. Load sharing is the simplest approach and carries over most directly from a uniprocessor environment, and its advantages are the load is distributed evenly across the processors, no centralized scheduler required, the global queue can be organized and accessed using any of the schemes.
So, are you done, Mr. Velasquez?
Yes.
So, about the load sharing discussion that you have just made recently, it's not all about advantages. There are also advantages of load sharing. Mainly, it can lead to bottlenecking. So, central queue occupies a region of memory that must be accessed in manners that enforces mutual exclusion. So, this exclusion can lead to bottlenecks. So, second, preemptive threads are unlikely to resume execution of the same processor. Caching can become less efficient. So, lastly, if all threads are treated as a common pool of threads, it is unlikely that all of threads of a program will gain access to the processors at the same time. The processes switches involved may seriously compromise performance. So, that's for the load sharing. Let's continue in gang scheduling. So let me present first. So, Mr. Velasquez, can you see my presentation?
Yes, Mr. Igot.
So, thank you. So, gang scheduling. Why should you be aware of it? Gang scheduling is a scheduling algorithm for parallel system that schedules related threads or processes to run the same time on a different processor. Usually, all threads should belong to the same processes, but they might also be from different process. Same process, but they might also be different processes. So what is the use of gang scheduling? Gang scheduling is mainly used to ensure that if 2 or more threads or processes communicate, they will always be ready at the same time. If gang scheduling is not used, then one might wait to send or receive message to another while it is sleeping. If gang scheduling is not usually used within a group of processes which communicate with each other, all communication event might suffer a context switch. So, what separates gang scheduling from other scheduling? Gang scheduling consider a task as a quantum and schedules them. A gang might require either multiple processes or threads or both. So, what does gang scheduling use as a data structure? Gang scheduling uses a outer out matrix as a data structure. It is a two-dimensional matrix which a row represents a time slice and a column represents a process or threads. The table shows how Osterhout matrix is formed and the job are scheduled. J1 to J4 represents gangs and P1 to P5 represents processes. So, as a gang scheduling deals with multiple processes and threads, there should be need for synchronization. So, these are concurrent gang scheduling, and shared scheduling system. So the synchronization module orchestrates all the scheduling. All the gangs run for a specific time interval, then it is interpreted and another gang can begin. In shared scheduling system, gangs with the same processes utilization are collected and executed for a fixed time period. It utilizes the internal clock system of each node it synchronizes using an NTP protocol. So there are advantages of the gang scheduling. It is closely related threads executes in parallel. Synchronization blocking is reduced, and less context switching. So there are types of gang scheduling. Bag of gang scheme. So this means all the gangs can be sent together to the system when a job is executed in the system. The execution can never be completed and unless all the gangs that belongs to the same BOG or bag of gangs is complete. So the next one is adaptive first come first serve or AFCFS. So in AFCFS or adaptive first come first serve scheme, once a job arrives at the system, the job will not be scheduled unless enough processors are available for the next execution of the respective job. In the largest gang served, first serve scheme, the tasks which correspond to the increasing job size are placed in a queue, with the task belonging to the largest gang scheduled first. Paired gang scheduling, on the other hand, is a method would represent the idea of matching pairs of gangs, one input and output based and one CPU bound. Each gang would assume that is working in isolation as they utilize different devices. So next, dedicated processor assignment. So dedicated processor assignment, so what is that? So it is when an application is scheduled, each of its thread is assigned to a processor that remains dedicated to the thread until the application runs to completion. If a thread of application is blocked waiting for I/O or for synchronization with another thread, then that thread processor remains idle. So there is no multi-programming of processors. So this is the application speed up as a function of number of threads. This graph shows that the threads, as it goes to 8 threads, the speed up increased, but as the thread increases, the speed up decreases. So that's for it. So dynamic scheduling is our next topic. So dynamic scheduling, it is a mechanism where thread scheduling is done by the operating system based on any scheduling algorithm implemented in OS level. So the execution order of threads will be completely dependent on that algorithm unless we have to put some control in it. This approach is superior to gang scheduling or dedicated processor assignment for application that can take advantage of it. Most of the work that uses dynamic thread scheduling has focused on shared memory systems. So just keep that in mind. So the positive and negatives of dynamic scheduling. So dynamic scheduling is scheduling faster in execution than static scheduling, since it's basically a free flyer without an intentional waits, joins, or etc. Dynamic scheduling is not aware of any thread, so this is the downside of it. So it is not aware of any thread dependencies. So if you followed above source and mentioned, you'll probably have the idea. So that's all. So the questions will be after the presentations, and that's all. Thank you.
Thank you, guys. Thank you, Mr. Retutal and Mr. Joaquin Resus, for inviting us here in your podcast. Bye, guys.
Bye.
Alright, so we just discussed multiprocessor scheduling. In our fast paced world, it is definitely crucial to make sure our systems remain stable despite the influx of large amounts of data. And to make sure processes are scheduled with an emphasis on correctness, depending on timing as well as functionality, we would need to have a much better understanding on real-time scheduling. I will now give the floor to my trusted engineers to explain further and more intricately.
Thank you, Vince. Hello, everyone. I am Engineer Catherine Sigaya, and this is the XCast podcast. Alright, so we're dealing with real time systems. But first, what really are they? So, real time systems deal with the results of the inputs or the operations involved in the system, as well as the deadlines or the times it was given to the users. Mainly, this can be seen in applications such as laboratory experiments, control systems, and in robots and rovers. To fully define what real-time systems are, they can be described in terms of explaining what real-time processes or tasks are. A hard real-time task should achieve the operation at the set deadline, or else there would be serious complications in the system. In short, these tasks are critical. An in-real-life example would be the deployment of a safety mechanism in the event of an accident, such as the airbag feature in car accidents. A soft real-time task, on the other hand, is not urgently needed to be done in the set deadline, yet they are still expected to give the results to the user. An example would be when you are watching a live stream. There might be delays in the video due to slow connections. Though it is preferable that you watch it in real time, it is acceptable to be behind the broadcast by a few minutes or so. Aside from being a soft task or a hard task, real-time tasks can be categorized as either periodic or aperiodic. Aperiodic tasks happen in random times and there might be no intervals between tasks. That is, the time is zero. They have soft deadlines and are not controlled by interrupts, and generally include the soft real-time tasks only. One example can be the filling up of activity logs. Periodic tasks, meanwhile, happen at set time intervals and are repeated over a time period. They have hard deadlines and generally include the hard and soft real-time tasks. An example is the radar scanning you can see in plane instruments. To note, a real-time system's operation lies on the short-term task scheduler. The scheduler should be able to achieve the hard real-time tasks to completion or its starting operation. And as much as possible, the majority of the soft real-time tasks, too, should achieve in the same circumstances. Now, since we finally defined what real-time tasks are in terms of real-time systems, we can determine the characteristics of real-time systems. The characteristics of real-time systems are as follows: determinism, responsiveness, user control, reliability, and fail-safe operation. Determinism refers to the execution of the processes in fixed and predetermined intervals and focuses on how long it is there before the operating system acknowledges the interrupt or task. This will be expanded later. Responsiveness refers to the duration at which it performs the tasks or interrupts and works hand in hand with determinism. This will be expanded by the next speaker. Determinism and responsiveness together make the response time to the said tasks and is essential for real-time systems due to the deadlines imposed by users and the data. User control pertains to the distinction of the soft and hard tasks, its needed characteristics, the collocation that tasks be, whether they will be in the memory or not, the algorithms needed to perform the operations, its type of urgency, and many more. Reliability talks about the performance and security in the event of system failures, wastage in resources, and in grave circumstances, the loss of human lives. Fail-soft operation refers to data and capability preservation as a response in the event of corruption or system failures. It speaks of what the system does to address the problem, whether to correct the error or continue running while attempting to reduce the severity of the problem. Stability is essential in doing fail-soft operations and that most of the high-priority tasks are still met, even if there are few less critical tasks that aren't met. To expand determinism, this pertains to the guarantee or sureness of the task's completion within the set deadline. This characteristic takes note of the speed of the acknowledgement of the task and the needed capacity it takes to execute the said task while keeping in mind the set required time or deadline. That's it for determinism. By the way, these are the sources I used. So proceeding myself is Engineer Stephen Tao. Please go ahead.
Thank you, Engineer Kathy. That was a wonderful presentation. As she said, I am Engineer Stephen Matthew Tao, and I'm here to discuss the features of real-time operating system and the types of scheduling. These are the features of real-time operating system. Fast process or thread switch. It means that the real-time system must be quick and be able to prioritize certain processes. Small size. Due to its minimal functionality, it allows the system to focus on a specified task or processes. Next, the ability to respond to external interrupts quickly. Real-time systems are tailored to do one or specific set of things as quick and reliable as possible. Multitasking with inter-process communication tools such as semaphores, signals, and events. The use of special sequential files that can accumulate data at a fast rate. Preemptive scheduling based on priority, which we'll talk about later. Minimization of intervals during which interrupts are disabled. Delay tasks for fixed amount of time. And special alarms and timeouts. Real-time scheduling has many scheduling models. Let's talk about the common four models. The round-robin preemptive scheduling, priority-driven non-preemptive scheduling, priority-driven preemptive scheduling, which is combined priorities with clock-based interrupts, and the immediate preemptive scheduling. The round-robin preemptive scheduling. The round-robin scheduling is the preemptive process scheduling algorithm. Each process is provided a fixed time to execute. Once a process is executed for a given time period, it is preempted and another process executes for a given time period. Round-robin scheduling is simple, easy to implement, and starvation-free. Round-robin scheduling can be applied to other scheduling problems, such as data packet scheduling in computer networks. As you can see here, the round-robin scheduling, the real-time process is added to the run queue, which means that the previous process has to be executed first in a given time period before being executed. Hence the name run robin, because each process awaits their turn. Next one, priority-driven non-preemptive scheduling. Priority scheduling is a non-preemptive algorithm and one of the most common scheduling algorithms in batch systems. Each process is assigned a priority. A process with high priority is to be executed first, and so on. Processes with same priority are executed on first-come, first-served basis. Priority can be decided based on memory requirements, time requirements, or any other resource requirement. This scheduling is better than round-robin because it gives high priority to the real-time process. However, it has to run completion of the current process before executing. This could lead to a delay of several seconds if a slow low priority tasks were executing at a critical time. As we can see here, after the current process is completed, the real-time process is executed next because of its high priority. Next is priority-driven preemptive scheduling. It's combined priorities with clock-based interrupts. This scheduling is the same as before, but it is now preemptive, meaning that the current process does not have to run completion, and the real-time process will be executed based on the preemption point. Preemption points occur at regular intervals. When the preemption point occurs, the current running process is preempted if the real-time process is a high priority, and it will be preempted in the next clock. This scheduling is good for some real-time systems, but it will not suffice for more demanding applications. Lastly, the immediate preemptive scheduling. The real-time process is preempted and executed immediately. Just like the previous scheduling, the current process does not have to run completion, and the real-time process will be executed. However, there is no preemption point. The operating system responds to an interrupt almost immediately. And that is everything for me. And following myself is Mr. Engineer Clyde Guerrero.
Thank you, Engineer Steven. Good morning, everyone. I am Senior Engineer Clyde Guerrero, and I will be discussing about real-time scheduling. For my part of the discussion, I will be talking about classes of real-time scheduling, deadline scheduling, preemption, period and aperiodic scheduling, and lastly, rate monotonic scheduling. First, I will discuss about the classes of RTS algorithms. It has 4 classes. The first class is the static table driven, second is static priority driven preemptive, third is dynamic planning based, and lastly, dynamic best effort. Static table driven. It performs a static analysis of feasible schedules of dispatching, which result is a schedule that determines at runtime when a task must begin execution. It is also applicable to tasks that are periodic. Input to the analysis consists of periodic arrival time, execution time, periodic ending deadline, and relative priority of each task. The scheduler attempts to develop a schedule that enables it to meet the requirement of all periodic tasks. This is a predictable approach, but one that is inflexible, because any change to any task requirements requires that the schedule be redone. For example, earliest deadline first. Static priority driven preemptive. It is a static analysis that is performed but no schedule is drawn up. This analysis is used to assign priorities to tasks so that a traditional priority driven preemptive scheduler can be used. One example of this approach is the rate monotonic scheduling algorithm, which assigns static priorities to tasks based on the length of their periods. For the dynamic planning based, it is determined at runtime rather than offline prior to start of execution. An arriving task is accepted for execution only if it is feasible to meet its time constraints. One result of the analysis is a schedule or plan that is used to decide when to dispatch this task. An attempt is made to create a schedule that contains the previously scheduled task as well as the new arrival. If the new arrival can be scheduled in such a way that its deadline are satisfied and that no currently scheduled task misses a deadline, then the schedule is revised to accommodate the new task. For the dynamic best effort, no feasibility analysis is performed, but when a task arrives, the system assigns a priority based on the characteristics of the task. The system tries to meet all deadlines and abort any started process whose deadline is missed. Typically, the tasks are aperiodic and so no static scheduling analysis is possible. With this type of scheduling, until a deadline arrives or until the task completes, we do not know whether a timing constraint will be met. This is the major disadvantage of this form of scheduling. Its advantage is that it is easy to implement. For the next chapter, we will be talking about deadline scheduling. It is designed with the objective of starting real-time tasks as rapidly as possible and emphasize rapid interrupt handling and task dispatching. Generally, not concerned with sheer speed, but rather with completing tasks as the most valuable times. Its priorities provide crude tool and do not capture the requirement of completion at the most valuable time. Information used for deadline scheduling. Ready time. It is when time tasks must become ready for execution. Starting deadline. It is when time tasks must begin. Completion deadline. It is when time tasks must be completed. Processing time. It is when time required to execute the task to completion. Resource requirements. It is resources required by the task while it's executing. Priority. It measures relative importance of the task. Subtask scheduler. It is a task may be decomposed into a mandatory subtask and an optional subtask. Preemptive scheduling. In this type of scheduling system, the process priorities are assigned. The RTS always executes the process with the highest priority first. Lower priority processes can be interrupted in the middle of execution to allow a higher priority process to execute. Once the higher priority process completes execution, the lower priority process can then continue executing from the point where it was interrupted. When starting deadlines are specified, then a non-preemptive scheduler makes sense. Example, if task S is running and task Y is ready, there may be circumstances in which the only way to allow both X and Y to meet their completion deadlines is to preempt X, execute Y to completion, and then resume X to completion. Periodic scheduling. A simple and efficient approach to scheduling real-time tasks is the use of a periodic server in a static preemptive scheduling algorithm. Periodic tasks, including the server, are scheduled to meet their deadlines according to the knowledge of their periods and computation times. Periodic tasks are regular arrival times and the hard deadline. So in this table, we have two periodic tasks, task A and task B. For the arrival time, it takes 10 milliseconds to process each sample of data from process A and 25 milliseconds to process each sample of data from process B. The execution time between process A and so on is 10 milliseconds, and in process B, it takes 25 milliseconds. The deadline of each task in process A is 20 seconds, 40 seconds, 60 seconds, and so on. And for process B is 50 milliseconds and 100 milliseconds, and so on. We can see on the table that A1 arrives first, followed by B1. But since A has priority, it comes first on the column 2. And since it's the second process free, B1 takes the next process. Then since A2 is the next priority because it's A, it is followed by B1 and so on. And since A3 is next, it is placed on the next process on T40, time 40, and then since it hits its deadline B1, then it is missed. Then on the third column, B has priority. Since B has priority, then it is placed first, and A1 is missed, then followed by A2 and A3. Then on a periodic scheduling. A periodic task have irregular arrival times and either soft or hard deadlines. The real-time task that occurs at any random time is known as a periodic real-time task. Between two aperiodic real-time tasks, the time interval may be even 0. Soft real-time tasks are generally aperiodic real-time tasks. It is also possible that these tasks may occur frequently, or there might be a large time interval between two aperiodic real-time tasks. We can see on this aperiodic table that the requirements are arrival time and the starting deadline. We can see on the second column, earliest deadline. The first deadline is A, followed by B, C, D, and E. A is placed first because it is the first on the line. followed by B, but B is missing because A took the process 10, and so on. On the third column, earliest deadline with unforced idle times, we can see that B is placed first because A is not yet ready. And why is it not ready? Rate monotonic scheduling. It is a priority assignment algorithm used in real-time operating systems with a static priority scheduling class. The static priorities are assigned according to the cycle duration of the job. So a shorter cycle duration results in a higher job priority. Rate monotonic analysis is used in conjunction with those systems to provide scheduling guarantees for a particular application. Following myself is Engineer Brian Arnoco. Please proceed.
Hi, my name is Brian Arnoco, and I'm going to talk about a task set with RMS. For RMS, the highest priority task is the one with the shortest period, the second highest priority task is the one with the second shortest period, and so on. When more than one task is available for execution, the one with the shortest period is serviced first. If we plot the priority of tasks as a function of the rate, the result is a monotonically increasing function, which is presented in the figure, hence the name rate monotonic scheduling. This next figure represents the periodic task timing diagram. It illustrates the relevant parameters for periodic tasks. Priority inversion. Priority inversion is a phenomenon that can occur in any priority-based preemptive scheduling scheme, but is particularly relevant in the context of real-time scheduling. In any priority scheduling scheme, the system should always be executing the tasks with the highest priority. Priority inversion occurs when circumstances within the system force a higher priority task to wait for a lower priority task. A simple example of a priority inversion occurs when a lower priority task has locked a resource, such as a device or a binary semaphore, and a higher priority task attempts to lock the same resource. The higher priority task will be put in a blocked state until the resource is available. If the lower priority task soon finishes with the resource and releases it, the higher priority task may quickly resume, and it is possibly that no real-time constraints are violated. Unbounded priority inversion. A more serious condition is referred to as unbounded priority inversion, in which the duration of priority inversion depends not only on the time required to handle a shared resource, but also on the unpredictable actions of other unrelated tasks as well. This figure shows the sequence that caused the priority inversion. T3 begins executing. And T3 locks semaphore S and enters its critical section. Next, T1, which is higher priority than T3, preempts T3 and begins executing. Next, T1 attempts to enter its critical section, but is blocked because the semaphore is locked by T3. T3 resumes execution in its critical section. T2, which has a higher priority than T3, preempts T3 and begins executing. T2 is suspended for some reason unrelated to T1 and T3. T3 resumes. It then leaves the critical section, unlocks the semaphore. T1 and preempts T3, locks the semaphore, and enters its critical section. In this set of circumstances, T1 must wait for both T3 and T2 to complete and fails to reset the timer before it expires. In practical systems, two alternative approaches are used to avoid unbounded priority inversion, which is priority inheritance protocol and priority ceiling protocol. The basic idea of priority inheritance is that a lower priority task inherits the priority of any higher priority task pending on a resource that they share. This priority change takes place as soon as the higher priority task blocks on the resource. It should end when the resource is released by the lower priority task. This figure shows that the priority inheritance resolves the problem of unbounded priority inversion, which is illustrated in the figure back figure represented on the unbounded. The relevant sequence of events is as follows. T3 begins executing. T3 locks semaphore S and enters its critical section. T1, which has a higher priority than T3, preempts T3 and begins executing. T1 attempts to enter its critical section but is blocked because of the semaphore is locked by T3. T3 is immediately and temporarily assigned by the same priority as T1. T3 resumes execution in its critical section. T2 is ready to execute, but because T3 is now a higher priority, T2 is unable to preempt T3. T3 leaves its critical section and unlocks the semaphore. Its priority level is downgraded to its previous default level. T1 preempts T3, locks the semaphore, and enters its critical section. T1 is suspended for some reason unrelated to T2, and T2 begins executing. In the priority ceiling approach, a priority is associated with each resource. The priority is assigned to a resource is one level higher than the priority of its highest priority user. The scheduler then dynamically assigns this priority to any task that accesses the resource. Once the task finishes with our resource, its priority returns to normal. Linux scheduling. The three Linux scheduling classes are Sched FIFO, Sched RR, Sched Other. Within each class, multiple priorities may be used, with priorities in real-time classes higher than the priorities for Sched Other class. The default values as follows. Real-time priority classes range from 0 to 99, inclusively, and Sched Other classes range from 100 to 139. A lower number equals a higher priority. Non-real-time scheduling. The Linux 2.4 scheduler for the Sched Other class did not scale well with increasing number of processors and increasing number of processes. The drawbacks of this scheduler include the following. The Linux 2.4 scheduler uses a run queue for all processors in a symmetric multiprocessing system, SMP. This means a task can be scheduled on any processor, which can be good for load balancing but bad for memory caches. The Linux 2.4 scheduler uses a single run queue lock. Thus, in an SMP system, the act of choosing a task to execute locks out of any other processors from manipulating run queues. The result is idle processors awaiting for release of the run queue lock and decreased efficiency. Preemption is not possible in a Linux 2.4 scheduler. This means that a lower priority task can execute while higher priority task waited for it to complete. A relationship to real-time tasks. Real-time tasks are handled in a different manner from non-real-time tasks in the priority queues. These three considerations should apply. The effect of these rules is that the switch between the active queue list and the expired queue list only happens when there are no ready real-time tasks waiting to execute.
So, that is it. I hope our listeners found value in us discussing about multiprocessor and real-time scheduling. I would like to thank my team for taking the time to share their expertise regarding the topics, and a big shout out to our special guest, Jordi L. De La Cruz, for also partaking in this podcast despite his hectic schedule. If you want to get posted on everythingos.com and HubOS related, you can follow us on our social media pages on your screen right now. For audio-only listeners, you can follow us at OS, that's OSD, and at HubOS, that's HUBOS, on all social media platforms. Back to you, Joaquin.
Thank you for the lovely presentation, OS.com, and thank you once again for being a guest at our show, Engineer Retutal. It was great having you, and I'm sure everyone viewing this podcast has learned so much. So everyone, that is all we have to show for today, and we have to go. That is this week's XCast podcast, all things tech, all things games, and all things software related. I'll see you all again next week with another star guest. Cheers.